2 trillion galaxies, millions of civilizations older, smarter, and more powerful than us. Not one has ever arrived here. Not because they gave up, because the universe made arrival physically impossible. So, why is reaching Earth completely hopeless for any alien that tries? Before we start, a gentle subscribe helps this channel keep growing. Now, let's begin. Try a simple experiment tonight. Step outside, find a clear patch of sky. Look up and pick 2 stars that appear closest together, 2 bright dots nearly touching like the eyes of something enormous staring down from the dark. Your brain will process them instantly. 2 objects, close together, same flat surface, small, measurable gap between them. That is the exact moment the universe begins lying to you. Those 2 stars might be 50 light years apart. One could be a dim red dwarf burning quietly 6 light years away. The other, a massive blue giant blazing from 800 light years out. They are not neighbors. They do not share the same region of space. They belong to 2 completely different corners of the galaxy, and your retina compressed all of that immensity into a clean, flat, comfortable illusion without triggering a single warning signal in your mind. The night sky is not a window looking out into the universe. It is a painting glued flat against the ceiling. This is not a flaw in human vision. Eyes were shaped by millions of years of evolution to solve a very specific problem, staying alive on one planet, spotting predators in tall grass, judging the distance of a spear throw, measuring the depth of a river before crossing. The human visual system is extraordinarily good at all of those things. But when the task shifts from estimating how far away a tiger is to estimating how far away a star is, that same system fails completely and fails in silence, without any signal that something has gone wrong. The strangest part is not that we cannot feel those distances. The strangest part is that we do not know we are failing to feel them. When people look up at the night sky, the brain automatically fills the gaps between stars with imaginary roads, invisible bridges, interstellar corridors connecting one bright dot to another the way cities connect along a highway. And from that illusion, every conversation about alien visitors has ever been born. Every film, every debate, every theory about UFOs arriving from distant worlds. All of it built on a foundation that is simply not true. The Pacific Ocean stretches roughly 17,000 kilometers at its widest point. The distance to the nearest star, not a far star, the nearest one, is about 40 trillion kilometers. If the Pacific Ocean were shrunk down to 1 centimeter, that interstellar distance would still be more than 2 billion times longer. 2 billion Pacific Oceans placed end to end, and that is not even a long journey by the standards of the universe. That is just the first step out the front door. The universe was not built at a scale human beings can feel. It was built at a scale human beings can only calculate, and the results of those calculations always produce the same reaction. This cannot possibly be real. But it is real. Do we truly understand what we are talking about when we casually say the words nearest star? The nearest star, the one that sounds like it is just 1 step away, holds a number inside it that will shake every assumption about space travel to its foundation. Alpha Centauri, 4.24 light-years away. That sounds close. 4.24, a small number, something you can say in under a second. But a light-year is not a human unit of measurement. It is the universe's unit. And the universe did not design its measuring system for the comfort of a primate species on a small planet. 1 light-year equals roughly 9.46 trillion kilometers. Multiply that by 4.24, the result is approximately 40 trillion kilometers. If you counted every single kilometer, 1 per second, without sleeping, without stopping, it would take more than 1.2 million years to finish counting. The counting would have had to begin before the first ancestors of modern humans existed. But the number that truly matters is not the distance itself, it is the time required to cross it. Voyager 1, the fastest and most distant spacecraft humanity has ever built, travels at roughly 61,000 kilometers per hour. At that speed, it could travel from one side of Earth to the other in under a minute. Impressive by human standards, nearly motionless by the standards of the universe. At that speed, the journey to Alpha Centauri takes 73,000 years. 73,000 years. The first agricultural civilizations appeared roughly 12,000 years ago. Writing was invented around 5,000 years ago. The pyramids at Giza were built approximately 4,500 years ago. Every empire, every war, every scientific discovery, every work of art that humanity has ever produced fits inside 12,000 years. Voyager needs 6 times that entire span just to reach the nearest neighbour in our solar system's local area. And Alpha Centauri is not even the interesting destination, it is simply the closest one. Sirius, the brightest star in the night sky, sits 8.6 light-years away, roughly double the distance. Vega, the brilliant blue star in the constellation Lyra, is 25 light-years out. Betelgeuse, the red giant, marking the shoulder of Orion, lies approximately 700 light-years from Earth. These are all considered nearby stars, local stars, the galactic equivalent of the houses on the same street. Each step outward does not increase the number gently. It jumps. It leaps by factors that make all previous comparisons feel outdated the moment the new one arrives. Light itself, the fastest thing in the universe, nothing moves faster, nothing ever will, needs 100,000 years to cross the width of the Milky Way. Not a spacecraft, not a rocket, light. And the Milky Way is just one of an estimated 2 trillion galaxies scattered across observable space. If the nearest neighbour already takes 73,000 years to reach, what exactly is the rest of the galaxy? And those 73,000 years do not belong to some old, outdated, primitive machine. That number belongs to the fastest object humanity has ever created, and it is flying through space right now at this very moment. On September 5th, 1977, a rocket lifted off from Cape Canaveral, carrying a 722-kilogram probe and something deeply human, a golden record etched with sounds and images of Earth-ocean waves, birdsong, music from dozens of cultures, greetings in 55 languages. A letter dropped into the cosmic ocean, addressed to anyone who might ever find it. That was Voyager 1. It has been flying ever since. 47 years of continuous travel, never stopping, never slowing, aimed outward into the dark. It is currently the most distant human-made object in existence. By any measure of human achievement, it is extraordinary. It has also covered less than 1/4 of 1 light-year. To put that plainly, after 47 years of uninterrupted flight, Voyager 1 has completed less than 0.002% of the journey to Alpha Centauri. The nearest star, the closest possible destination. Here is where the picture becomes almost comedic in its cruelty. Voyager is essentially a delivery driver who set out from 50,000 years before the Common Era, is still somewhere on the road, and whose tracking app has been showing on the way for longer than our entire species has existed. The package has not arrived. The package will not arrive for another 72,000 years. Nobody who ordered it will be alive. But the timeline is not even the most important part. Voyager has no braking system. When it finally reaches the vicinity of Alpha Centauri, roughly 73,000 years from now, it will not stop. It will not slow down. It will pass through that star system in a matter of hours, sweep past whatever planets might orbit there, and continue sailing into the void beyond a frozen relic, tumbling through permanent darkness with no destination and no purpose. Remaining, the golden record will go with it. The ocean waves, the bird song, Bach and Chuck Berry, and greetings in 55 languages, drifting through interstellar space at 61,000 kilometers per hour, getting farther from every living thing with every passing second. There is a real chance no one will ever play it. Not because the universe is empty, but because the universe is so large that even a message traveling for tens of thousands of years may never cross paths with the mind capable of receiving it. Voyager is our greatest physical reach into the cosmos. It represents the absolute edge of what human engineering has achieved in nearly 50 years of continuous effort. And in the context of interstellar distance, it is a grain of sand that has barely rolled off the beach. If the fastest thing humanity has ever built is this, if this is the ceiling, then what does interstellar travel actually mean in practice? But the speed and the numbers are not the most unsettling part. The most unsettling part comes when the full picture of the Milky Way is placed at its true scale, because that is when every remaining assumption collapses completely. There is a way to make the Milky Way feel real, not by looking at it, not by reading about it, by shrinking it. Imagine compressing the entire Milky Way galaxy down to the size of the continental United States, coast to coast, border to border. Every star, every gas cloud, every spiral arm scaled down into that familiar shape on a map. At this scale, each individual star becomes a grain of fine dust. Not a marble, not a pebble, a speck so small it is barely visible to the naked eye under good lighting. Our Sun is one of those specks. Alpha Centauri is another one. At this scale, those two specks sit approximately 10 centimeters apart, about the width of a hand. 10 centimeters. That sounds manageable. That sounds almost touchable. But now look at what 10 centimeters actually represents in this picture. That gap between two dust grains, the gap that looks like nothing on a table, is 40 trillion kilometers in reality. It is the distance that Voyager 1 needs 73,000 years to cross. The gap that looks like a finger's width on this shrunken map is already beyond the reach of every technology humanity has ever built. And that is just the distance to the nearest grain. A civilization orbiting a star 1,000 light-years from Earth would sit in a completely different state on this map. Not across the room, not across the building, a different state entirely. Kansas, perhaps, while the Sun sits somewhere in Virginia. A civilization 5,000 light-years away lands on the opposite coast. The full width of the galaxy stretches from New York to Los Angeles, 100,000 light-years coast to coast. Now, look at science posters showing the Milky Way. Brilliant spiral arms packed with hundreds of billions of glowing points. It looks dense. It looks crowded. It looks like a neighborhood teeming with life pressed close together. That image is one of the most misleading pictures in all of science communication. The Milky Way is not defined by its stars. It is defined by the emptiness between them. The stars are the exception. The void is the rule. If every star in the galaxy were the size of a grain of dust on this continental map, the average distance between neighboring grains would still be measured in meters, not centimeters, not millimeters, but meters of empty floor between each. Nearly invisible speck. Most of the map is blank. Most of the space contains nothing at all. Now consider what this means for two civilizations trying to find each other. Both of them are dust grains on a continent-sized map. Neither one knows where the other is. Neither one can see across the distances involved. The electromagnetic signals they send out crawl outward at the speed of light, fading as they go thinning across volumes of space so enormous that by the time those signals reach another grain, they may be indistinguishable from background noise. The probability that two civilizations randomly positioned across this galaxy happen to be close enough, aimed correctly at each other, and broadcasting at the right moment to actually make contact is not low. It is not even very low. It is so close to zero that the word low feels generous. The galaxy is not a neighborhood. It is an archipelago of isolated islands, separated by oceans that have no surface, no bottom, and no shore on the other side. If the entire Milky Way compressed to the size of a continent still produces this kind of separation between neighbors, what does the phrase finding each other in the galaxy actually mean in practice? But distance is only half the problem. Because even if a civilization wanted to find us, even if they pointed every telescope they had in our direction, there is a physical reason they would not know we are here at all. Humanity has been broadcasting radio signals into space for roughly 100 years. Television transmissions, military radar, satellite communications, FM radio, all of it leaking outward from Earth at the speed of light in every direction, forming an expanding sphere of electromagnetic noise moving through the galaxy. That sphere is now approximately 200 light-years in radius. 200 light-years sounds significant. It is not. The Milky Way is 100,000 light-years across. Our radio bubble occupies a volume so small relative to the total galaxy that if the galaxy were the size of Earth, our entire detectable presence would be smaller than a grain of sand sitting somewhere on the surface. Less than 1/1,000,000th of the galaxy's total volume contains any evidence that humanity exists. The numbers become sharper when applied to a specific scenario. A civilization orbiting a star 1,000 light-years from Earth has not received our first radio signal yet. That signal, broadcast roughly 100 years ago, has only traveled 100 light-years so far. It still has 900 light-years left to cover. At the speed of light, It will not reach that civilization for another 900 years. From their perspective at this moment, Earth is electromagnetically silent. It always has been. Their telescopes see our sun as one ordinary yellow dwarf among hundreds of billions. Nothing special, nothing unusual. No indication that anything worth travelling across the galaxy for is happening on the third rock in that unremarkable system. But suppose they are patient. Suppose they wait 900 years and the signal finally arrives. What do they receive? Not a clear greeting, not a beacon, a whisper so faint it barely registers above the background hum of the cosmos. Radio signals obey a precise physical law. Their strength weakens with the square of the distance travelled. A signal that is strong at its source becomes 4 times weaker at double the distance, 9 times weaker at triple, the distance 16 times weaker at quadruple. By the time Earth's strongest broadcasts cross 1,000 light-years, the energy arriving at any given point in space is billions of times fainter than the natural radio noise produced by stars, pulsars, and the cosmic microwave. Background. Detecting it would require a receiver of almost incomprehensible sensitivity. And even with such a receiver separating a human radio signal from the surrounding electromagnetic chaos of the universe is like trying to hear a single person whispering in the middle of a hurricane. Not difficult, not challenging, functionally impossible. This is not a failure of alien technology. This is not a limitation that a more advanced civilization could engineer around. It is physics. Electromagnetic radiation spreads. Energy dilutes. Distance is not forgiving. For most of the galaxy, Earth does not exist. Not as an enemy, not as a mystery, not as a question worth asking, simply as a fact that has not arrived yet, and when it does arrive, will arrive too quietly to hear. If we are electromagnetically invisible to the overwhelming majority of the galaxy, does the question "why haven't they come to visit" actually make sense as a starting point? But set all of that aside. Suppose they know we are here. Suppose somehow, against all of these odds, a civilization locks onto our location and makes the decision to come. That is the moment the universe places an energy bill on the table, and what is written on that bill has never been paid easily by anyone anywhere in the entire history of the cosmos. Suppose the distance problem is accepted. Suppose a civilization looks at 40 trillion kilometers and says, "We understand the scale, we accept the cost, we will build faster ships." That is a reasonable starting position. That is what ambition looks like. Then the universe hands over the bill. To accelerate 1,000 kilograms, roughly the mass of a small car, no passengers, no life support, no return fuel, just a bare metal frame with instruments to 10% of the speed of light, requires an amount of energy equivalent to 14 full years of continuous output from a large nuclear power plant. A facility that costs billions of dollars to construct, that powers approximately 1 million homes, running at maximum capacity every hour of every day for 14 consecutive years. All of that energy funneled entirely into pushing one car-sized object to a speed that still means a 42-year trip to the nearest star. That is the entry price. That is the minimum. Now adjust for reality. A spacecraft that reaches its destination at 10% of the speed of light will pass through the target star system in a matter of hours unless it slows down. Deceleration requires the same energy as acceleration applied in reverse. The bill doubles. Add a crew and life support systems and radiation shielding and water and food and navigation equipment. The mass climbs from 1,000 kilograms to hundreds of thousands. The energy requirement scales accordingly. Add a return journey. Multiply again. What began as 14 years of nuclear output becomes centuries of it all, directed at a single mission for a single ship aimed at a single destination. The most energy-dense fuel theoretically possible is antimatter. When matter and antimatter meet, they annihilate each other completely, converting 100% of their combined mass into pure energy. No chemical reaction, no nuclear fission, no fusion process comes close to this efficiency. Antimatter is the absolute ceiling that physics permits, the ultimate fuel, and humanity has produced approximately 20 nanograms of it across the entire history of particle physics research. 20 nanograms. A quantity invisible to the naked eye, undetectable on any kitchen scale, insufficient to power a light bulb for 30 minutes. Producing a single gram of antimatter using current technology would cost roughly $25 trillion and require energy inputs equivalent to thousands of power plants running for years. Producing the 500 kilograms needed to push even a small probe to 10% of the speed of light would demand energy and resources so far beyond current civilization that placing a timeline on it becomes meaningless. The entire global economy redirected entirely toward antimatter production using every watt generated on Earth would need millions of years to accumulate that quantity. And 500 kilograms of antimatter is the fuel estimate for the bare minimum mission: no crew, no return, no braking at the destination. This is not a technological limitation waiting for a smarter engineer. The relationship between mass velocity and energy is not a design problem. It is not a manufacturing challenge. It is a law written into the structure of reality itself, confirmed by every experiment ever conducted, applying equally to every civilization that has ever existed anywhere in this universe. The floor is set by physics. Technology can only determine how efficiently that floor is approached. It cannot go below it, ever. If pushing a car-sized probe to 10% of the speed of light already costs 14 years of nuclear output, what does a real crewed vessel actually require? And that is only the energy problem, not yet the crueler problem. Underneath it, the one that persists, even when energy is available, a mathematical trap that every rocket in the universe falls into the moment it tries to go faster. There is an equation that has haunted every rocket engineer since it was first published in 1903 by a Russian mathematician named Konstantin Tsiolkovsky. It is not complicated. It does not require advanced physics to understand. But what it describes is a trap so elegant and so absolute that no civilization bound by the laws of physics has ever escaped it. The trap works like this. To go faster, a rocket needs more fuel. More fuel adds more mass to the vehicle. More mass means the rocket now needs even more fuel to accelerate that additional weight. More fuel adds still more mass, which requires still more fuel, which adds still more mass. The loop feeds back on itself, and the fuel requirements do not grow in proportion to the desired speed. They grow exponentially. For chemical rockets, the kind that have carried every human being who ever left Earth's surface, this feedback loop becomes catastrophic long before interstellar speeds are approached. A chemical rocket achieving 1% of the speed of light would require a fuel load heavier than the entire observable universe. Not heavier than Earth, not heavier than the solar system, heavier than everything that has ever been observed to exist. The number is not impractical. It is mathematically impossible by a margin so vast it exits the territory of meaningful discussion. Nuclear propulsion improves the situation. A nuclear pulse drive the theoretical concept that involved detonating a continuous sequence of nuclear explosions behind a spacecraft could theoretically reach perhaps 3 to 5% of the speed of light. Impressive. Also requiring a spacecraft the size of a city and a stockpile of nuclear warheads that would dwarf every arsenal on Earth combined. And 3 to 5% of the speed of light still means a journey of nearly 100 years to Alpha Centauri alone. Even the most advanced ion drives currently in development, the most efficient propulsion systems humanity has ever tested, would need millions of years to reach Alpha Centauri. Millions. Not thousands. Millions. The barrier is not engine design. It is not materials science. It is not manufacturing capability. The barrier is the mathematics of moving mass across interstellar distances. Tsiolkovsky's equation does not care how intelligent the engineer is. It does not soften for more advanced civilizations. It applies to chemical rockets, nuclear rockets, ion drives, and every other propulsion concept that carries its own fuel, because carrying fuel means carrying mass, and carrying mass means the loop never ends. There is one proposed escape from this trap. Instead of carrying energy onboard, fire the energy from a fixed location and push the spacecraft from behind. A laser sail. A massive reflective sheet attached to a tiny probe, accelerated by a ground-based or space-based laser array of enormous power. No onboard fuel, no feedback loop. The energy source stays home. The Breakthrough Starshot initiative proposed exactly this. In 2016, a gram-scale probe lighter than a paperclip pushed by a laser array, producing 100 gigawatts of power reaching 20% of the speed of light, arriving at Alpha Centauri in roughly 20 years. 1 gram, lighter than a paperclip, requiring the focused energy output of an entire industrialized nation for 20 years of travel. With no way to slow down at the destination, if every solution to going faster demands exponentially more fuel or exponentially more external power, is there actually any exit from this loop? There is one partial escape: fire the energy from home and leave the fuel behind. It sounds like the perfect solution. But removing the fuel problem does not remove what lies underneath it, the one enemy that cannot be outrun, outspent, or out-engineered. Time, 10% of the speed of light. That is the benchmark serious discussions of interstellar travel always return to. Not because it is easy. It is almost unimaginably difficult to achieve. But because at lower speeds, the journey durations stop being challenges and start being geological events. At 10% of the speed of light, a spacecraft travels roughly 67 million kilometers per hour, fast enough to cross the diameter of Earth's orbit around the Sun in under 3 hours, fast enough to reach Neptune from the Sun in about 2.5 days. By any standard, a human being can feel this is blindingly fast. At this speed, a journey to a star 1,000 light-years away takes 10,000 years. 10,000 years. The entirety of recorded human history, every written word, every built structure, every named civilization, from Sumer to the present, fits inside approximately 5,000 years. This mission requires double that span just for the outbound leg. The civilization that launches the ship in the year 2000 would need to maintain continuous institutional commitment, sustained funding, active navigation support, and coherent mission purpose until the year 12,000. By which point, every language currently spoken on Earth will have transformed beyond recognition. Every existing government will have risen and fallen many times over, and every person alive today will have been dead for 97 centuries. The communication problem compounds this into something approaching total futility. A radio signal travels at the speed of light. A ship traveling at 10% of the speed of light is moving in the same direction as its outbound communications, which means signals sent home travel faster than the ship but still take years to arrive. A message sent from a ship 100 light-years into its journey takes 100 years to reach home. A reply takes another 100 years to return. A single exchange of information, one question, one answer, requires 200 years of waiting. Discover a critical malfunction on year 10 of the voyage. Transmit an emergency message home. Wait 11 years for it to arrive. Wait for engineers to analyze the problem and devise a solution. Wait another 11 years for the response to travel back. By the time repair instructions arrive, 22 years have passed. The crew members who sent the original distress call are now significantly older. Some may be dead. The institutional knowledge needed to solve the specific problem may have passed with them. This is not a communication inconvenience. It is the permanent severing of any meaningful connection between the mission and the civilization that launched it. Within decades of departure, the ship is alone. Within centuries, it is an orphan. The crew cannot be guided, cannot be rescued, cannot be reinforced. Every decision, every crisis, every catastrophic failure must be handled with whatever is already on board and whatever knowledge already exists within the walls of the ship. Relativistic time dilation offers a partial consolation. At 90% of the speed of light, time passes more slowly for the crew. A 100-year journey in the outside universe would feel like roughly 44 years aboard the ship. At 99%, the crew experiences only about 14 subjective years for every 100 years that pass at home. They arrive younger than the universe expected. But time dilation solves the problem for the travelers, while catastrophically amplifying it for everyone else. The crew experiences a manageable journey. The home civilization experiences an absence measured in centuries. Everyone the crew ever knew is dead. The world that launched them has had 100 years to change, forget, collapse, or move on entirely. Can any civilization sustain the will, the resources, and the institutional memory required to support a mission lasting 10,000 years? The honest answer to that question leads directly to the only solution ever proposed in Ernest's place: an entire society aboard the ship, and let generations replace each other until someone finally arrives. But that solution carries inside it a tragedy that nobody wants to look at directly: the The concept is elegant in its simplicity. If no individual can survive the journey, send a population. Build a vessel large enough to house a self-sustaining community. The first generation lives, works, has children, and dies aboard the ship. Their children do the same, and their children's children. Generation after generation born inside metal corridors, living entire lives between the stars, passing the mission forward like a relay baton across centuries and millennia until the final generation arrives at the destination their ancestors chose for them. On paper, this solves the survival problem. In practice, it opens a catalogue of failures that compound with every passing decade. Start with biology. Genetics research suggests that a population needs a minimum of roughly 10,000 individuals to remain genetically viable across many generations, maintaining enough diversity to avoid inbreeding, sustaining the variation needed to adapt to new environments, preserving resilience against disease. 10,000 people, not a brave crew of volunteers. A small city with all the complexity, the conflict, the resource demands, and the social dynamics that a small city requires. Housing, feeding, and sustaining 10,000 people in a sealed environment for thousands of years requires a vessel of enormous size and mass. That mass feeds directly back into the energy equation discussed earlier, compounding costs that were already beyond staggering. But population size is the easiest problem on this list. In 1991, 8 people entered a 3-acre sealed habitat in Arizona called Biosphere 2. It was the most ambitious closed ecosystem experiment humanity had ever attempted, designed to be entirely self-sustaining, recycling all air, water, and food internally. It had the advantage of Earth's gravity, natural sunlight through transparent panels, and a fully functioning magnetosphere overhead. It had the entire scientific resources of a modern civilization available just outside the glass walls. It lasted 2 years before oxygen levels dropped to dangerous lows and external intervention became necessary. 8 people, 3 acres, 2 years. On the surface of Earth, a generation ship would need to sustain 10,000 people in a sealed metal container, moving through hard vacuum bombarded by cosmic radiation. With no sunlight, no natural gravity, no magnetic shielding, and absolutely no possibility of outside assistance. For thousands of years, without a single critical system failing in a way that could not be repaired from within. Now consider the social dimension. Imagine the ship 500 years into a 10,000-year voyage. The original crew is 20 generations dead. Nobody alive has ever seen a sky. Nobody has ever felt wind. Nobody has ever stood beside an ocean or watched a sunrise that was not projected onto a screen. The mission was designed by people so distant in time, they have become mythological figures whose actual intentions are interpreted rather than remembered. Imagine explaining to the 200th generation that the entire purpose of their existence, every hour of every day, of their entire lives, is to travel toward a rock that none of their ancestors for 200 generations ever actually saw, to complete a journey none of them ever chose, and that there is no alternative. There never was. That is not a mission. That is a sentence handed down across 2 centuries. 5,000 years and the situation moves beyond tragedy into something stranger. Language has drifted across hundreds of generations into forms the founders would not recognize. The original mission documents exist in a script nobody can read fluently. The purpose of the journey has been reinterpreted so many times through so many ideological and religious lenses that competing factions hold completely incompatible beliefs about where the ship is going, why it is going there, and whether the destination is a physical place or a spiritual metaphor. Some believe arrival is sacred. Some believe the journey itself is the point. Some believe the entire story of an origin world and a destination planet is mythology, that the ship has always existed and will always exist, and that the concept of stopping is heresy. Is it right for one generation to decide that every generation following them must spend their entire lives inside a metal tube on a journey they never chose and cannot escape? But all of this, the distance, the energy, the time, the human cost, still has not reached the final argument, because one rebuttal remains untouched, that a sufficiently advanced civilization would simply find a way around all of it. And this is exactly where physics speaks its last word. At this point, a familiar argument always arrives. It arrives in conversations, in comment sections, in late-night debates between people staring at the same stars. It sounds reasonable. It sounds humble. It sounds like exactly the kind of open-minded thinking that serious people should embrace. It goes like this: you are thinking too small. You are projecting human limitations onto beings who may have had millions of years to advance beyond us. A civilization ancient enough, intelligent enough, powerful enough, they would simply find a way. They always find a way. To examine this argument properly, there is a framework worth knowing. In 1964, Soviet astronomer Nikolai Kardashev proposed a scale for classifying civilizations based on total energy consumption. A Type 1 civilization harnesses all the energy available on its home planet. A Type 2 civilization captures the entire energy output of its host star, wrapping it in a theoretical structure called a Dyson sphere, collecting every photon, every watt, every joule the star produces. A Type 3 civilization commands the energy output of an entire galaxy. Hundreds of billions of stars, all harnessed, all directed. Humanity currently sits at approximately 0.7 on this scale. We have not yet captured all the energy our own sun sends toward Earth, let alone the sun's total output. A Type 2 civilization commands roughly 4 times 10 to the 26th watts of continuous power, a number so large it has no intuitive meaning. A Type 3 civilization multiplies that by 400 billion. These are godlike energy budgets by any standard the human mind can process, and none of it changes the speed of light by a single kilometer per hour. This is the point the advanced civilization argument consistently misses. More energy does not rewrite the laws of mechanics. The minimum kinetic energy required to accelerate a given mass to a given velocity is fixed by the relationship between that mass, that velocity, and the constant speed of light. These are not variables. They do not adjust based on who is doing the engineering. A Type 2 civilization can generate the required energy far more easily than we can. They can afford the fuel bill more comfortably, but they cannot pay a smaller bill. The bill is set by physics, not by the size of the civilization's bank account. Lifting 1 kilogram 1 meter against Earth's gravity requires approximately 10 joules of energy. This is true whether the lifting is done by a human hand, a pulley system, or the most sophisticated robotic arm ever designed. The mechanism changes. The energy requirement does not. Technology determines how efficiently that minimum is approached. It does not determine how far below that minimum you can go. The floor is fixed, forever. A Type 2 civilization launching a large interstellar vessel, say 10 million kilograms, accelerated to 10% of the speed of light, would consume energy equivalent to a measurable fraction of their star's output sustained over days or weeks. They can afford it. But launching thousands of such vessels, the kind of systematic exploration program needed to visit even a small fraction of nearby star systems, would strain even a stellar energy budget in ways that make such programs effectively impractical. And every single ship still faces every other constraint. Every ship still takes thousands of years to arrive. Every ship still carries crews through radiation and void. Every ship still loses contact with home within decades of departure. More energy does not compress the distance. More energy does not stop the clock. Here is the version that makes the point impossible to miss. A Type 3 civilization controls the energy of an entire galaxy and still has to sit down and calculate whether it makes sense to send a ship on a 10,000-year journey toward a planet it cannot confirm is worth visiting. The energy is available. The physics is not negotiable. That is like being the wealthiest entity in existence and still having to genuinely think before buying a one-way ticket with no return date, no guarantee of arrival, and no way to call home once you leave. The bank account grows larger. The price of the ticket does not change. If even a civilization commanding the full power of a star must pay the same physical price as everyone else, what does the phrase advanced enough to overcome the limits actually mean? There is still one argument left untouched, not more. Energy, but something more radical, bending space-time itself. Warp drives, wormholes, the shortcuts that physics does not explicitly forbid on paper. But what hides inside those equations is the part worth examining carefully. Science fiction has made certain ideas feel inevitable. Given enough time, enough intelligence, enough technological progress, humanity, or something like humanity, will eventually build a warp drive, will eventually thread a wormhole, will eventually find the shortcut that bypasses all the brutal arithmetic of interstellar distance. These ideas feel inevitable because they appear in enough stories told with enough confidence. But feeling inevitable and being physically possible are two entirely different things. Start with the warp drive. In 1994, physicist Miguel Alcubierre published a paper describing a theoretical mechanism for faster-than-light travel that did not violate special relativity. The idea was precise contract space in front of the spacecraft, expand space behind it. The ship itself sits inside a bubble of flat spacetime and does not technically move through space at all, space moves around it. Since the speed of light limit applies to objects moving through space, not to space itself, moving the math appeared internally consistent. For a brief moment, it looked like a genuine door. Then the requirements became clear. Sustaining the warp bubble requires exotic matter material with negative energy density. Not matter that is cold. Not matter that is rare. Matter that weighs less than nothing. Matter that gravitationally repels rather than attracts. No such material has ever been observed anywhere in the universe. No current theoretical framework produces it in usable quantities. Its existence is not merely unconfirmed, it is unclear whether the laws of physics permit it at all. The energy calculations made the situation more explicit. Early estimates of the energy required to generate and sustain an Alcubierre warp bubble came out to roughly the mass-energy equivalent of the entire observable universe. Later refinements with optimized geometries reduced this estimate dramatically. After the most aggressive theoretical optimizations currently known, the energy requirement still equals approximately the mass energy of Jupiter, the largest planet in our solar system, converted entirely into energy. Converting Jupiter entirely into energy. As the fuel cost for one trip, wormholes face identical objections from a different angle. An Einstein-Rosen bridge, a theoretical tunnel connecting two distant points in space-time, does exist as a solution within the equations of general relativity. The mathematics permit it. The physics, however, ensures that any naturally forming wormhole collapses almost instantaneously, far too quickly for any object to pass through. Stabilizing one requires exotic matter with negative energy density. The same material that does not exist has never been observed and may not be physically possible. And even if exotic matter existed, and a traversable wormhole could be held open using it to travel faster than light, would almost certainly violate causality. The foundational principle that causes precede effects. If faster than light travel between 2 points is possible, then through a precise application of special relativity arrival, before departure becomes mathematically achievable. Time travel becomes a consequence. Most physicists regard this as strong evidence that traversable wormholes cannot exist in a universe that operates the way this one does. Special relativity does not say that nothing currently moves faster than light pending future upgrades. It says that the structure of spacetime makes it impossible for anything with mass. As any massive object approaches light speed, the energy required to push it further approaches infinity, not a very large finite number, actual mathematical infinity. Infinity cannot be reached, cannot be exceeded, cannot be engineered around. The speed of light is not a speed limit posted on a highway that a faster vehicle could theoretically ignore. It is the geometry of the room, and the room is what everything is made of. When every theoretical shortcut requires materials, the universe may not permit energies that dwarf entire planets and conditions that violate the foundational logic of cause and effect. Where exactly is the line between theoretical physics and science fiction wearing a math costume? When every road leads back to the same answer, the question stops being whether they can come here. It becomes something deeper, something that points not outward into the galaxy, but directly back at us. The silence is the thing people cannot quite explain. The universe is approximately 13.8 billion years old. Stars have been forming for most of that history. Planets capable of supporting life may have existed for 10 billion years or more. If intelligent civilizations arise with any regularity across galactic history, and there is no physical reason they should not, then the galaxy has had an enormous amount of time to fill with minds, signals, ships, and evidence. And yet the sky is quiet. The searches are quiet. The frequencies are quiet. Decades of systematic listening have returned nothing unambiguous. This is what is known as the Fermi paradox, the gap between how many civilizations should exist and how many we can detect. The silence. Many explanations have been proposed. Maybe life is rarer than expected. Maybe intelligent life almost always destroys itself before reaching interstellar capability. Maybe advanced civilizations deliberately go quiet. Maybe they are communicating on frequencies or through methods we have not yet conceived. Every explanation carries its own weight of uncertainty. But there is one explanation that requires no exotic assumptions, no self-destruction, no deliberate hiding, no technological incompatibility. The explanation that follows directly from everything examined in the preceding pages. The universe is structured to keep its inhabitants apart, not as punishment, not by design in any intentional sense, simply as a consequence of the physical constants that happen to define this particular cosmos. The speed of light happens to be finite, energy happens to be conserved, entropy happens to increase. Distances between stars happen to be measured in units that make crossing them a civilizational undertaking rather than an exploratory one. Every civilization that has ever existed, every mind that has ever looked upward and wondered, has faced the same arithmetic, the same energy bills, the same timescales, the same communication delays, the same entropic decay of ships and crews and institutional memory across impossible spans of time. The math does not favor meeting. The math enforces isolation. Thousands of civilizations may be burning right now across the Milky Way, each one surrounded by the same void, each one staring at the same unreachable stars, each one reaching the same conclusions through its own version of physics, its own version of particle accelerators and telescopes, and late-night calculations that all terminate at the same wall. The silence of the cosmos is not evidence that those fires do not burn. It is evidence that the cathedral is too large and the flames too brief for the light of one to reach the other before it goes out. And here is where the question turns. If the universe has built this isolation equally for every civilization, if the wall stands at the same height for a species that has existed for 1 million years as it does for a species that has existed for 100, then the question is no longer about them. It was never really about them. Earth is not a prison. A prison is a place you are kept against your will, waiting for release. Earth is something different. It is the only confirmed location in the observable universe where the things that matter most to the beings living here are actually possible. Conversation, memory, music, the particular angle of afternoon light through a window, the weight of another person's hand. None of these things require interstellar travel. All of them require this planet in this condition for as long as it remains capable of supporting the lives being lived on it. The question was never really why they have not come. That question assumed the interesting things were out there waiting to be visited. But every piece of physics examined here points to the same quiet conclusion. The interesting things are here, and they are fragile, and the time available to experience them is shorter than it feels. If the universe built the same prison for every civilization without exception, what is the one thing that remains entirely within reach? Candles burn in a vast cathedral. Each one lights for a few seconds, casting its small circle of warmth, then goes dark. The darkness between them is not empty. It is simply too wide for any flame to bridge. The question was never why the other candles do not find their way here. The question, the only question that was ever really worth asking, is what to do with the light in the brief moment while it still burns.